Let's try it. Tutorial world. Okay, so tutorial world, fine. So our goal is, you see, you know how this works, right? You have objects here, goals here. The goal is x times y plus z. And notice how it highlights, like, is it x times y, like, what's PEMDAS, right? What's the order of operations? Well, you just hover, and it knows that it's x times y first, and then x times y is being added to z. So the hovering will tell you, if you're ever confused about that, the hovering, has information, and then there's an equal sign. So what do you do when it's exactly the same thing on both sides of the equal sign? RFL, and that's what it says. If you read this text, it says RFL. So REFL is a tactic that says whenever what your goal is x is equal to x, whenever it's the same things on both sides, there's an axiom that says that can be cleared. So I hit RFL, and there's nothing to do. Great, done. Next. So far, so good? Okay, that was easy. Now, our goal is 2y is equal to 2 times x plus 7, and our assumption is the hypothesis H of type y is equal to x plus 7. So how do I get it to rewrite this, replace y with x plus 7? That's the rewrite tactic. So that's what it's going to say up here. The rewrite, you could spell out the whole thing, rewrite. I think it'll take rewrite H, but we have not unlocked the tactic rewrite yet, but we have the shorthand RW rewrite H. Okay, great. Rewrite H, what it did is it replaced the instance of y here with what was on the right-hand side. Rewrite is directional. So it goes from the left-hand side to, if it finds the left-hand side, it replaces it with the right-hand side. Now what? Ref. Done. Next. So far, so good? Okay. Yada, yada, yada. If the successor of A is B, then the successor of A is B. Oh no, there's nothing to do here. We can rewrite H. That'll replace this successor of A with B. So I thought we were up to something involving induction. We're not there yet. Okay, so now the new goal is successor of B to successor of B. It replaced successor of A with B. And you've closed this with beautiful. Okay. A plus the successor of 0 is equal to the successor of A. Okay. Now, what do we know? So now we need a few more things. We have some lemmas here. Let's see. Oh, there we go. That's better. And that's better. Okay. So our lemmas are add suck. What is add? Let's see. It's here. Add suck is the lemma that says given two numbers, A plus the successor of D is equal to the successor of A plus D. Okay, so that's a lemma that we have access to. So if I say rewrite add suck, what it will do is it will look for a pattern of something plus the successor of something. I don't have to specify that you should look in the goal for A and 0. I could specify A and 0, and it'll do it. But I could also, let's see, there's editor mode if you want to work with it similarly to how you would work with it in a regular way. I'll try to stay in play mode. So let me undo that. So I've undone this move that I just did. So if I just rewrite add suck without specifying that it's A and 0, it'll still look for that pattern. Does that make sense? And it'll match that pattern. And so now I have successor of A plus 0 is equal to successor of A. How do I get rid of the fact that it's A plus 0 there? Add 0, exactly. Now it's add 0, not 0 add. So you want to see addition, then 0. That's the pattern that it'll find. So if I rewrite add 0, now it has the last step, which is going to be REFL. By the way, we could have done this in one step. We can rewrite these two things in combination. So let me undo them again. And what did we do first? We did add suck, and then we did add 0. And you can do them in combination, and then REFL. We'll close it. Okay? That's tutorial world. Addition world? Any questions? Let's do it. Addition world. Okay. Now we're going to start induction. So we know we have this add suck, but we don't have suck add. I'm sorry, we have add 0, but we don't have 0 add. So this would be the theorem 0 add, that if you take 0 and add it to something, you get n. Okay, so we always run induction on, well, it can be subtle, but let's just run induction. So this is induction on the letter n. N is the thing that we're gonna, n is a natural number. Natural number starts at 0, and then the successor of a natural number is as a natural number with, and then what do you want to call the variable that you're going to induct on? We could call it n, we could call it d, we could call it Bob. It will let us, let's see, NHN, it will let us, so now we have two goals. Where is the other? Here we go, further goals. So we have one goal, which is 0 plus 0 is equal to 0. We have another goal is that we'll get to that. That'll be the induction step. So it does allow us to do n, but we could have said induction n with d and then the induction hypothesis on d, hd. Okay, which is what it suggests. Okay, so our goal is 0 plus 0 equals 0. How are we going to solve that? Yes, now we have addition 0. We're trying to prove 0 addition, but now we have addition 0. We know how to rewrite that. Add 0. And now we have 0 equals 0 as the goal, which we ruffle. Okay. Automatically, it has moved us to our second goal. Our second goal is the induction hypothesis. We assume that 0 plus d is d. D is a natural number. We're trying to prove that 0 plus the successor of d is the successor of d. How are we going to do that? Exactly. It's add suck, if you remember, is the, I guess it doesn't tell you, oh, does it? No, it's not telling you what the lemma is. Fine, whatever. It's that it looks for addition and then the successor. So if I rewrite add suck without specifying anything further, it moves the successor to the outside. Now 0 plus d. Wait a second, we're trying to prove that 0 plus d is d. But wait, but we have the induction hypothesis, which is exactly HD. So if I rewrite the induction hypothesis, HD, now I have ref. So far, so good. Okay. Why is addition associative? Just from the definition of addition, it's not at all clear that it is, in fact, associative. This is the kind of thing you do in like intro to proofs course. You're like, what do you mean? You have to prove that addition is associative? You're insane. Of course it's associative. Why? When you go from the axioms, you really have to understand why. Okay, now, which variable should we induct on? Induction on A, induction on B, induction on C, those are all possible tactics. Yes. Exactly. Because addition is, this is what the hint is saying right here. Addition is defined. We have the add 0 lemma. So addition is defined on the right. So we want to use the rightmost variable to do the induction. So let's do induction on C with NHN, DHD, CHC. Let's just do CHC. Okay, so now again, we have two things. A plus B plus 0 is equal to A plus B plus 0. What do we want to do with that? Yeah, B plus 0, we can turn and something. You see, it's even without parentheses. In what order is it doing it? By hovering, you can see in what order it is. So it's doing A plus B first and then plus 0. So it's going to find that plus 0. If we do add 0, I think it's just going to do the first one. Yes, it just did the first one. There's another instance of it. So we can rewrite add 0 again. I don't think it'll let us repeat. You can do repeat add 0, which means it'll do it as many times until it's okay. So we could have done that in one line with a comma, for example. And now it's REFL. Okay, so adding 0 on the right is associative. Now we have this as the induction hypothesis. Assume that we have associativity for A, B, and C. Why is there associativity for A, B, and the successor of C? Now what? Okay, what is that going to do? Perfect. So it's going to find the first instance of plus successor and pull that successor outside. Now what? Yeah, we have to do it again to pull this successor all the way out. So we'll rewrite add suck again. Now we have to do it again. Let's rewrite add suck again. Now we can do the induction. So rewrite HC. And now it's REFL. So we could have done, let me undo those 4 moves. And we could have done add successor, add six. How many did we need? 3. Add successor, and then HC. All in one fell swoop, and then REFL. Okay. All right. Y is, we have add successor. This is successor add. If you have successor of A plus B, that also can pull out. That's not, again, in my mind as a kid, I'd be like, this is a waste of my time. But there, you can see now with the computer, like, why is this true? Okay, what should we do? Induction on A or on B? On the rightmost variable, because that's where things are defined. Induction, B with BHD, if you like. Okay, Y is the successor of A plus 0 equal to successor of A plus 0. Beautiful. Let's do add 0. 0 twice. And REFL. Should I scroll down? You can't see that. That's better. Assuming we have it for A and D, why is it true for the successor of D? The first one is going to find this plus sign and successor. The second one is going to find that plus sign and successor. Now induction hypothesis, which we could have done again in one fell swoop. And now the 2 sides are identical. Okay, this is getting easy. Next level. Y is addition commutative? What do I do? Induction, B, on what? B with BHB. Okay, Y is left addition of 0 and right addition of 0. Add 0 and 0 add. REFL. Okay. Assuming that, why is this going to happen? Add suck. Good thing we proved these theorems. And HB, because that's going to be, we'll have successor of A plus B, successor of B plus A. We have the induction hypothesis and REFL. No goals. Okay. Gosh, the successor of N is N plus 1. But what is 1? 1 is a successor of 0. And there's a theorem that we need. Let's see, MyNat. Yes, here's the new theorem that just got added. I'm surprised it doesn't tell me what the theorem is. It just,
if you go into the editor mode and write in the tactic and hover over it, it'll tell you what it is, but it won't tell you that on the side.
Right.
Really stupid.
Yeah.
all right, well, it's in beta. Yeah. Sure. So you can do like a have my nat dot 1 eq successor of 0.
Then if you hover over it, it should
Yeah.
yeah.
So there it is. 1 equals successor of 0.
And that works.
Yeah.
It works like pretty much anything you throw in there if you play how it works.
Yeah. I don't know if we've gotten to the have. Yeah, it'll tell you theorem. I don't know if it'll work for apply. If you just write apply, I don't know that you can hover over it.
Oh, okay.
So
Really? Yeah, but it doesn't. Yeah, we haven't unlocked the tactic yet, but it tries to match goals. And okay, yeah, all right. Right. So what is 1? 1 by definition is the successor of 0. So let's rewrite that. Rewrite 1 equals successor of 0. 1 equals successor of 0. Now we have that. Add and then suck, and then add, and then 0. And now ruffle. Okay. Okay. What is this? This is add right com. So if I add on the right to A plus B, or if I add on the right to A and then add B, what do you want to do with this? Let's try that. Let's see HC. Okay. How come it's true when you have 0? Add 0. This will be add 0 applying to here. This will find the add 0 inside of this expression. So I think it's add 0 twice.
Oh, I was thinking the 0 added the 0 plus B.
But it's not 0 plus B, you see? In both cases, it's plus 0. It's A plus B in parentheses plus 0. Here it's A plus 0 in parentheses.
Oh,
And then plus B. So that's what the hovering lets you do. So that's why it's whatever it was. Rewrite add 0 and add 0. And now we have REFL. The other goal is the same thing, but now with add sucks. How many will we need? Add suck, that's going to pull this successor all the way out front. And add suck is going to pull that successor out a little bit. So let's do 2 of them and see what happens. So you see we have the successor all the way here. And here we have the successor, but not all the way out.
Sorry.
Good thing we proved that. And now it looks just like the goal, the induction hypothesis. So now I can write the induction hypothesis, and this 2 sides are identical. Okay, next. That was addition world, function world or multiplication world? Function world? Sure.
So I've already done a function.
Okay. Whatever you want, they're all good. Multiplication, let's do it. Okay, 0 times m is 0. We are given mul 0. And our goal is to prove 0 mul. So mul 0 is induction on m, exactly. We're told that multiplying by 0 on the right is 0, but not on the left. Okay, so induction m with MHM 0. Now I'm going to rewrite mul 0, which we have, and that's REFL. Our other thing is about suck. Now, what do we know about multiplication by suck? So what lemmas do we have here?
We got mul suck.
We've got mul suck, and we're multiplying the successor. Okay, so let's rewrite mul suck. And now we have this. Now we have the induction hypothesis, rewrite HM. And now we have either 0 add 0, either one. And now it's REFL. By the way, in real life, you would never use any of those. There are tactics that, this is just like for you to get used to working with Lean. But when you're actually in MATLAB and you have to prove any of these things, there are like you just say ring, and ring closes all of these goals. Yes.
So, for the thing that you just did.
Yes.
You have brackets around the induction thing, so how did it know when you ended induction?
What really happens is that,
I was looking at like prior stuff that the exact same previous stuff, and it was like, that had brackets around the like the hypothesis and the assumptions that you're making.
yes.
So like, where's that here?
Okay, so what is really going on is you no longer need brackets. The Lean4 way of doing this is, when I do this induction, I have 2 goals now. I have the goal of I don't know why I can't see this. Oh, there we go. I have to scroll down. I have one goal is 0 times 0 is 0, and then I have the further goal. In the Lean editor, you would see that as 2 separate goals on 2 sides. If you're in like VS Code or something. So what you would do is you would put a dot and you would say, I just want to work on a single goal And then everything has to be, oh God, it's all gonna break. I have to answer that question not within the natural number game.
Oh, so this is like a different,
This is not what working in Lean actually looks like.
oh, okay.
Okay, but it's similar enough. I mean, it's meant to teach you the basics, and then when you go into Lean itself,
Then everything will compile because something is screwed up on your system.
So does Lean4 have, still have count?
yes.
I see.
So instead of putting brackets around it, you would do that dot thing that I was trying to do, but it doesn't work in this version of it. So there are two goals. You can put brackets around the two goals and say, I only want to work on the first goal. Anyway, you're working towards the first goal. When you're done with the first goal, now we're on to the second goal. And it just automatically switches. The first goal was done by that raffle. Now I'm on the second goal. Now I'm working through the second goal. And there's the raffle that closes it. And I guess the second I close it, everything is programmed to disappear.
So is there any merit to like writing that theorem down in like Lean4 and then actually writing it in VS Code and like not in?
If you're in Lean4 with MathLib running, then this theorem is ring. So there are tactics that take care of all this nonsense. You don't, as a mathematician, you don't want to be doing 0 times m is 0. You want to be doing much higher level things.
Yeah.
So this is just for us to learn how Lean works. And then when you actually go to use it, you're never touching nonsense like this. You want to get right to contentful mathematics. Although that's not always possible immediately. Okay. How are we going to prove that m times 1 is m? We know what lemmas are we given? We are given anything about successor equals what? Okay. What do we know about multiplication? Okay, this is all we know about multiplication. Yes.
Oh, so you would do like rewrite mul 0, 1.
Mul 0, 1. Do you mean?
Or sorry, 0 mul.
Well, we're not. So if I try to rewrite 0 mul, we just proved. Let me go out of editor mode. So it looks for 0 mul looks for something at 0 times something, and it looks at the goal and says, I didn't find it. It failed. The rewrite failed. Okay, so let's undo that one. Whoops, I don't know what happened. Let's try something else. How about, first of all, let's get rid of the 1. It can't see through the 1 to the successor of 0, although really the real Lean can. But this is just for our benefit. Let's rewrite 1 is equal to the successor of 0. Okay, and now m times the successor of 0 is m. We have mul suck, the multiplication and then the succession. Rewrite mul suck. Will give us this. Now what? M times 0 is mul 0. I can't see. Rewrite mul 0. And now we have 0 and then add. Exactly. Everybody see that? Okay, next. Why is it true the other way? We could, there's a variety of ways of trying this one. What's another way? Like where you can use induction, because now it's something on the right. So I feel like you could do it either way, actually. Let's just see if induction is faster. Okay, what do I know about multiplying by 0? All 0. And then raffle. And how about the other way? Mul suck. Rewrite mul suck. Let's see if we can get it in one line. After mul suck, so imagine in your head what's about to happen. Multiplication by suck is going to turn into 1 times m plus m.
And then rewrite your HM.
Exactly. HM is going to turn that. Sorry, it's going to be 1 times m plus 1.
Mm-hmm. And then suck equal add 1. And then RFL.
You mean 1 is equal to, oh, suck is equal to add 1, exactly. So we have this new lemma, suck equal add 1, that the successor of a is a plus 1.
And that should give you m plus 1 equals m plus 1, and then
Cool? Yeah, you guys are getting good at this.
Does rewrite REFL not work?
REFL isn't a rewrite tactic. REFL is its own tactic.
REFL isn't a tactic, it's a term, right?
Yeah. You want me to go back?
Written as a tactic up there.
Oh,
Doesn't the new RW actually perform reference on? I think
Yeah,
not in this environment.
that's right. In Lean itself, when you do this rewrite and it notices rewrite is a little stronger than the rewrite of the natural number game, it'll just end it already.
because
So basically, like, you don't have to do work in.
You sometimes have to do REFL if you didn't get there by a rewrite. If the previous step was something other than the rewrite. Okay. Why do we have mul add? So mul add is what happens when it's the distribution property. Yeah, it's left distrib, whatever. There's a variety of, again, you shouldn't have to ever remember these things. You should know one thing, which is the tactic ring. And ring cancels, multiplies, does all kinds of this nonsense for you. Okay, multiplication distributes over addition. Why is this true? We could do induction. Is there something slicker we could do than induction? I'm not sure there is. Let's just do induction. What's that? Sure. Okay, what am I going to do with this?
Add 0.
Add 0. Add 0 will clear that 0, make it t times a. Mul 0. Mul 0 will make this thing 0, and then add 0. Can't see. And then add 0 will clear that. So that should get us down to REFL.
I have no clue what this happened.
Should I go back?
So like, why did you like, if possible, do you like explain each step like?
Yes. So I see addition of 0 plus 0. So if I rewrite add 0, what that will do, it'll look for the first instance of a plus sign followed by a 0, and it'll replace that by just a itself. A plus 0 is a. That's step 1. It's going to turn this into t times a. Then, so that's it. If I just do that by itself, that's all it does. T times a turns into t times a plus 0 turns into t times a. Then, but we're trying to do it all in our head. Then the next thing will be mul 0. Mul 0 will turn t times 0 into 0.
Yeah.
Mul 0. And now the last thing is I'm adding 0. So let's rewrite add 0. And that'll clear this plus 0 and just leave it as t times a. So we did those 3 steps in our head without seeing the goal update.
Okay.
And then REFL. Does that make sense? Okay, and now given that that's true down here, why is it true for the successor of B? Yes, add suck is going to move this successor out. Add suck is going to move that successor out.
Sure, so that would be the successor out to be t times the successor rate.
Exactly. You want to see it? Or can you imagine it? You want to see it?
Sure.
Okay, so there it is. T times successor rate.
I should honestly probably do it because I can't even see the goal.
Oh, okay, yeah.
That's fine. Awesome.
Come on over here. That's why I tried to, yeah.
Then apply a mul suck.
Okay. Mul suck and mul suck. You said apply, but apply is another tactic that we'll get to later. Okay, so we cleared both of those mul sucks. And now what? What were you going to say? Yes, yeah. So let's use the induction hypothesis. B. Okay, t times a is t times b plus t, and t times a is p.
And then mul assoc or add assoc.
Add assoc, yeah. Rewrite add associative. And there we go. REFL. Easy? Easy but simple, just how we like it. Let's go, go, go. Okay. Why is multiplication associative? Induction on the rightmost letter. Okay, rewrite mul 0, mul 0. So let's see, that'll turn this whole thing into 0. That'll turn this into 0. Another mul 0. And now we should have 0 equals 0. Okay, now what? Mul suck. That pulls the successor all the way out.
Also, like, Ruffle is like ending the brackets. I see.
Ruffle is if I have x equals x. Yes, if you like.
REFL is a
It-
term of type x equals x for any type x.
Yes, implies true, implies done.
That makes a lot of sense.
So now let's do mul suck again. So now we have A times the successor of B times C. Let's do mul suck again. You see, so we only need one to pull this to the other side because this is A times B together. Now we need to pull this one out twice. And now what? Let's see how much we can do in our head. We'll have A times B times C is the successor of A times B times C.
No, you also, yes, apply your induction.
Now,
Oh.
Yeah, because you don't necessarily know that the
Oh, I
parentheses work.
see, you still have the parentheses on the right side.
yep,
Improving.
Yeah, got it.
okay.
What happens if you put REFL inside the rewrite? Is that-
Uh-oh, what happened? It failed. It failed.
Like one of our.
Oh, let's see. Okay, it's failing before. Let's try it one at a time. So, oh, it did. What I said was complete nonsense. Mul suck does not pull the suck out. It drops the suck and replaces it with A times B times C plus A times B. And same thing here. So, right? It's not addition. So it made it A plus B plus C plus an A times B. And over here, it's going to do, let's do it again. So two of them are good. It makes it this. Now I want to distribute the A, left distribute the A. What was that called here?
It's mul add.
Yeah.
That sounds right. Let's rewrite mul add.
You left it upstairs.
And now we're almost done. Now we need induction.
Really should have.
And we're done. Ruffle. Okay.
I've been starting to see like the differences in syntax. It makes a lot more sense.
Okay, the successor of A. So we had mul suck, now we're proving suck mul.
Okay, oh, you're proving something else you can't use it. Oh, that's unfortunate.
That's the hard thing about, yeah, you can't use the theorem that you're trying to prove.
Yeah.
Again, you would never do any of these things. Okay, rewrite mul 0. I see another mul 0. And I see an add 0.
And then.
Ruffle. Okay, let's do these one at a time. Or should we try to so what is this going to do? It's going to take this suck B and do suck A times B
Plus suck A.
plus suck A.
You only have to do one mul suck.
No, because here I have a suck B, here I have a suck A. I know this, so let's rewrite this. Let's rewrite the induction hypothesis. And now I have A times B plus successor of A. So we're very close. We need to do mul suck on this part. Huh? So now I have A times B plus A plus the successor of B. We're kind of,
Some people add one and then a whole bunch of messing around to get appearance supposed to say.
yeah. Is there anything that we can do to make it a little nicer?
So, if the sub A, if you add sub, that will be sub of B plus add. Right?
Yes.
Then. If you add sub again, and then get sub A and B, and we have addition.
Okay, we can pull out a whole bunch of add sucks. Let's pull the suck all the way out, right? That's what you're saying?
So just, well,
Like I'm just pulling the sucks all the way out?
I guess
And-
I wanted to do this.
Oh, you wanted to do associativity first?
Guys,
Okay,
So on the left side, then we're gonna be looking at the B plus sub A term.
okay. So tell me what to do. Add com or,
Both sides.
okay,
Purple all the way up to both, right?
yep.
Okay.
Now what?
And then now we do want it to be associative, so we're looking at the last two,
Uh-huh,
for both of them.
uh-huh,
And now we use commutativity.
uh-huh. Add com twice. Oh,
Just once.
BA, should we specify which one we're doing?
yes,
Yeah.
that's how we'll be able to get to that. So let's rewrite add com.
Undo the previous step. and then-
Oh, undo the previous step you like?
Yeah, and then add com BA.
Okay, great. Add com BA or AB. BA, it'll find this one, AB, it'll find this one, whichever one you want to flip. Does that make sense? And now they're the same.
Yeah.
And now, great. Okay, add mul is distribution on the right. So induction with A or B. Yeah, T. That's the rightmost variable. With THT. Okay, mul 0, mul 0, mul 0, and then add 0 or 0 add should do it. And the other one, okay, we're gonna need a mulsuck. Okay, we need another mulsuck here on each of them.
And apply HT as well, or rewrite HT.
Uh-huh, HT. HT will make this into that. And now we're almost done. It's just a matter of rewriting things. Let's see.
So
Huh?
with the BT plus A plus B.
Yeah, why don't we do an add a sock on both of them? So the associativity, we can get the A times T by itself because it's already okay. So let's do, now let's see, if I do the associativity, yeah, good. So it got the A by itself here. And then if I tell it to do the associativity, I think it's going to look at this associativity. Oh no, this one doesn't, that's already in that form. So it'll do this side.
Would it undo the one on the left?
No, if I do left add associativity, then it undoes associativity.
Oh, I
It's
see.
always looking for the pattern of addition followed by addition, not addition on the left followed by addition. So it's keeping track of the order of operations. Okay, great. So the ATs are isolated. Now I want to
Plus A plus B.
yeah, there's a variety of ways of doing this. We could commute this, put the B on that side, put the B on that side.
Yeah, you don't have to do it.
Yep, add com. Let's do AB. That'll flip this B and A. Then let's do another commutativity of B times T and B. Let's see. And now I can do let's get the B plus T on the end. I mean, there's such a
Wait, go back, left add, like, then just do left the sock on the BT, B plus A. So then now you're gonna be BT plus B, A, and then you flip, and then you're done.
okay, so tell me what do you want to do?
Left add a sock on BT and then B plus A.
On B times T and B plus A.
So that we can, so now we're gonna get the grouping of BT plus B and then plus A. and
Great.
then Swap those.
So watch this. I don't even have to tell it B plus A because there's only one place where there's a B plus T and a plus with more pluses after it. Okay,
And now you can just commute between, BT plus B and A.
between BT and A
BT plus B.
plus B,
And then.
and A.
And then you'll be done with that.
Okay, now that is perfect. Rafa. Great. Okay, so you guys are obviously very much getting the hang of this. Is that it for multiplication? Oh, and now multiplication commutes. Okay, induction on B with BHB. Rewrite 0 mol and mol 0. Raffle. And now what? Rewrite mol successor, successor mol. That gives us that. We have the induction hypothesis that multiplication flips. Rewrite the induction hypothesis. And now we're done. Okay. We have now proved that natural numbers are a commutative semiring. This is the last collectible. We don't, yeah. 8 minus 9. Do you know what 8 minus 9 is in the natural numbers? 0. 8 minus 9 is 0.
Yeah, yeah, I agree.
You'll get used to this. Okay. We're still in multiplication world. We have to prove that multiplication is associative. What should we do?
The only word we know.
The only word we know, induction C with CHC. Okay, mol 0, and I think I need one more mol 0. This mol 0 is going to make that a 0. That makes that a 0. This, I need one more. I need actually 4 of them. Right? To pull everything out. Oh, 3, I guess. That is 0. That's 0.
Just try the 3 and see what it says.
Yeah, 0, 0. Fine. We can go back and figure out why it was only 3 and not 4, like I thought. Suck mol. I mean mol suck. Mol successor. Now what? Ring would be nice, but we don't have ring. How about what is it? Add mol or something? We want to distribute this?
Yeah, mol add.
Mol add distributes, and let's distribute again. Mol add. Oops, rewrite. Oh, it's supposed to give me that bracket. Okay, now induction. Rewrite induction. And now the first 2 bits are the same, but the second 2 aren't. Mol com, let's specify which, A and B.
Then R.
Raffle. Okay. So now we add a lot of the lemmas you just proved to simp. Okay. It would really be ring. Should we do a little function world? Okay, let's do a little function world. So function world, this is really, really useful. It looks like it's just stupid logic, but actually it's very, very useful, as you'll see. So our goal is Q. We have P and P implies Q. So if I feed H, let's see, can I show it like this? Oh, it destroyed it. Have H is a function from P to Q. So if I give it an element of P, HP is an element of Q. And the goal is an element of Q. I call it an element, but really it's a term of type Q. So that's exactly what it wants. So exact HP.
Okay, yeah.
Closes it. Does that make sense? How we did that?
Then it's not the same, like, we want this proposition.
Yes. Yeah, you can think about it as proofs of propositions, or you can think about it as terms of type. So we want a term of type Q. HP is something that takes a term of type P. Takes a term of type P and gives you a term of type Q, and we fed it P. Okay. Uh-oh. Editor mode? No. So an example is a function from the we want a function from the naturals to the naturals. That's our goal. So whenever you have a function from something to something, you know, the first thing you could do is give me that thing. Give me the thing that you're starting with. So that's called intro. So the tactic is intro n, give me a natural number. Now we have our natural number, and we can give any natural number we like. We could exact it, we could exact n plus 1, we could exact n plus 7. And in fact, we could do both things in one fell swoop because we can give a function. So that's a function from n to n plus 2 or whatever.
Fun is not a tactic that.
Fun is not a tactic. Fun is the name of.
It's not something that gets done in this. I don't think that we were given fun.
You're not told what fun is, but the way to make a function is to say fun, give the variable name, maps to, and then whatever you want that to be. So that's all, that's done. Goal, you know, let me go out of editor mode. Oh, now you can't see. Let's see. So if I do exact, you can either intro n, or you can just give a function that takes n to 2 times n plus 17. Okay, does that make sense? Oh boy, we got a diagram chase. Good. Given an element of P, define an element of U. And we have all these maps. H maps P to Q, J maps Q to T, L maps T to U. Okay, so how do I give an element of U? HP gives me something in Q.
I is, no, J, yeah, J is going to give you that.
So this thing is going to be of type T. Maybe.
Yeah.
Okay. It wants the parentheses. Okay. All right. Pretty easy.
And I tried to do it without some first. There's like the where you do like the bar and the arrows like big.
Yeah.
things, And it was fine with that. Instead of
Uh-huh.
hearts.
Okay, let's do it a different way. Let's apply L. L is a theorem that says given T, you get U. You're trying to get U. So what would apply L do?
I would say that now this is in T.
Exactly. So we're working backwards, right? Apply L. Apply L. Now it changes the goal to give me something in T. Well, I could apply K, that'll say give me something in S, but then I can't give you something in S. I don't have a way of getting an element of S. So instead I'll apply J. So this is working backwards. Now we have Q. Now I apply H, and that says give me P, but I have P. That's called little p, exact P. That make sense? Okay. Now a map from P to Q implies P. What are we going to do? Why does P imply Q imply P? Why is that true? Yep, if I intro P, that gives me P, and it makes the goal Q implies P. Let's intro Q. Exactly P. Does that make sense? Okay. Fine. So we want to have a map from this to this to this to this. So if we know that H implies Q implies R, and we know that P implies Q, and we know that P, so P can be, so let's see, can we make a function version of this? We probably can. Should we do a function version? So let's take a function from PQR. So we're given PQR, and we're given PQ, and we're given P. And what should be a thing of type R? If I take PQ and I feed P into it, that'll give me, actually, that'll give me something in Q, but I don't want something in Q. If I take PQR, oh, I do want something. I do want P and Q and R. Okay, let's take PQR, because PQR is the thing that's going to give me, if I give it P and I give it an element of Q, it'll give me R. So I have to give it P, but I have P, that's just called P.
Why don't you just give it PQ and then give? Or are we not considering as a map from P, are we not considering as a map from the collection of maps that from P to Q to map to R?
It's the parentheses. So this is not P implies Q implies R. It's P implies Q implies R.
Yeah.
So I have to give it something in P, that's P. I have to give it something in Q. I have to give it a proof of Q, which is if I take P implies Q and feed it P, that'll give me Q. And then that should be an element of R. It took it. Let's just go out of editor mode and see what you see why this works? Should we do it a different way, a more standard way? This isn't what you're supposed to do. I'm sort of hacking it.
Actually, I mean. Maybe it's a little bit.
Okay, let's do it the most standard way too. So we should intro PQR, then intro PQ, then intro P. So that'll give us three things. One is P implies Q implies R, one is P implies Q, and one is P. And now we can build things up. So I can have something I'll call Q. Q is PQ given P. And now that's called Q. And now I can have, yeah, well, let's call it, well, let's not even give it a name. I just want you to see how this works. If I have PQR and I give it P, yes, exactly. So now I have something called this, which maps Q to R. So if I do this and I give it Q, that gives me a new thing called this. Oh, we don't have the tactic this yet. Fine. I'm not allowed to use this. Sorry. I have to give it a name. So let's call it QR is PQR given P. Fine. So it's kind of
You have to undo twice to get rid of the one you have.
Yeah.
This.
All right, let me copy. It doesn't matter that they're both called, that I have two things. One is called this and one is called QR. It doesn't matter. But in order to access that QR, I needed to give it a name. So QR, and I'll give that Q. That'll be an element of R. And now exact R. Okay, so that's the longer way to do it. All right. Next, and maybe last, I don't know how long people want to stick around. Let's do the last one. So we have a function from this to P to F. Should we do it in one fell swoop? An exact. So it's going to be a function. I'll take PQ, I'll take QF, and I'll take a P. And how am I going to get an element of F? The QF is what will get me F if I can give it an element of Q.
Q would be
PQP. Cool. Okay. PQ implies Q implies empty. And implies P implies empty. So the way you say not P is equivalent to P implies empty, or P implies false. All right. So let's do this one a little slowly. So let's intro PQ. We'll intro Q empty. PQ, then Q to empty, QE, then P. Okay. So we're supposed to construct an element of the empty set. Of course we can't. So the suggested line is apply H. If we apply H, they assume that we called it H, but we didn't. We called it QE. So let's apply QE. And now it says, give me an element of Q. Oh, good. We know how to do that. Exact PQP.
So thinking of it as like Q implies empty being not Q.
Yes.
Would say apply Q, like apply QE that's like your proof of like not Q.
Yeah, it's almost contraposition. You're given P implies Q, and you're asked to prove that not Q implies not P.
Yeah.
So you say, well, okay, let's say Q was true by contradiction. Then, or rather, let's say P was true by contradiction, then P implies Q means that Q is true, and that's a contradiction. That's logically equivalent. All right, last one. Oh God. Oh yeah, I'm in editor mode. That's why you can't see it.
Don't do this. Don't do these in editor.
Intro A. No, we're not going to start with intro A. We're going to give an exact. Exact. So we can get from A to B. So that's F1 of, do I have A? Do I have an, what do I have an element of?
You don't have any elements, that's why you need intro A.
Right. I need a function from A to, now I have an element of A.
On big A.
I want little a, which will be of type big A. Yeah, which you can think of as a proof of the fact of big A or term of type big A. So from little a, I can get to B. Let's see, let's go backwards. L, what are different ways I can get to L? I can get there from I can get to from J or from G. G I can get to from F I can get to from E I can get from B I can get to from A.
But then you get to J from G from F9.
Yes.
Yeah.
And then G from F and F from, so we could do a whole bunch of applies. There's like 100 different ways to do this. We can, let's try to do it in one line. So given A, now let's go forward. I can do F1, F1A is of type B. From B, I can get to E with F2. So now this is an element of E. I want to get to F with F5. I'm at F5, I'm at F, so I'll use F8 to get to G.
F9 to get to J.
F9 to get to J. Nah.
F11.
F11 to get to
I.
I.
Then F15 close.
And then F15 to shred it all down. Okay, so just so we can see it, this is it. You give me an element of A, I'll apply F1, F2, F5, F8, F9, F11, and F15. Okay, good enough? That's it for function world, and others are similar and left to your enjoyment.